Hi class, we're on 21.3 and this is types of radioactivity. Has a lot of slides to it. Most of them are examples of problems. So I try to give as many examples as I had. I've taught this section in a different chemistry, which is not as as difficult as this chemistry is. It's for a different type of for non-chemistry majors is what it is. And I took some of the slides from that lecture because I felt like it was just the problems are broken down a little bit easier, I think, to help some people understand this. So there's a lot of slides on this one, but it's mostly just problems. Okay, so natural radioactivity. Radioactivity comes from unstable nuclei, and the particles that are emitted are to help it become stable, which then changes it to another atomic or element. So this is found in carbon, hydrogen elements with atomic numbers 20 and higher. Defined as nuclei in which nuclear forces cannot offset the repulsions between the protons. And again, anything that emits these small particles of energy, that's radiation. So radiation and this is from a slide from this other class. We covered alpha, beta, and positrons and gamma rays in that one. With this one, we're going to have one more, but we're still going to cover these. So radioisotope. You have already learned about isotopes in another chemistry, but we're going to look at radioisotopes. So what is a radioisotope? Simple. It's an isotope that emits radiation. And it can be one or more isotopes of an element. And it includes the mass number. That's how you know you're dealing with an isotope in the first place. So in this case, you know you're dealing with an isotope when you have the mass that is attached to it. But you also have a formula here so we can see what this is. We have mass number. So if you see it set up like this, the top is the mass number, which is the protons plus the neutrons makes up the mass number. We have the atomic number, which is on the bottom. And then we have the symbol of element. So if you look at periodic table, the symbol of the element and the atomic number shouldn't change. The only thing that will change is the mass number depending on what isotope you're looking at. So this is just giving you the general formula. I thought I would introduce first one that makes sense, that you look at this and hopefully it comes back to you. And if it doesn't, this is a good review. Z stands for the atomic number. So you see it here. This is what you're seeing right here is 53. The mass number is the symbol is A. And then the chemical symbol is X. So when you see something that's referred to as A, that's the mass number. Z is the atomic number, and X. And I have no idea where they got these from. I don't. Number of neutrons is calculated by subtracting the atomic number from the mass number, or you add the protons plus the neutrons. That gives you the mass number if you look at it that way. And when we're discussing nuclear properties, we call the nucleus nuclide, and nuclides are identified by a symbol with the mass number and atomic number. Okay, so let's do an example here. How many protons and neutrons are there in an isotope with this aluminum? So this aluminum has a mass of 27 and it has an atomic number of 13. So which of these would that match up to? So if we look at this, it wants to know how many protons and neutrons. So at a given, we already know that we have 13 protons. So it's either going to be A or D. It's not going to be B or C because this bottom number, remember if we look at it here, is the atomic number, which equals protons. So this number minus this number would tell us how many neutrons we have. Excuse me. So 27 minus 13 is 14. So that's going to make our answer D. So if you're not remembering isotopes, this is a good review, or you should look back or even just go online and search isotopes. It's not difficult. It doesn't really change. I've given you the general formula and you should be comfortable with looking at that and knowing what you're dealing with. Okay, so this is also another slide from my other lecture. You can see what stable isotopes, and then there's radioactive isotopes. So you can see magnesium, the one that we're familiar with, is a stable isotope, but there are radioactive magnesium isotopes. There's a 23 and a 27. Iodine has iodine they use for thyroid problems. And there's a stable one, and then there's radioactive one, and then uranium has no stable one, but it does have, of course, radioactive ones. Okay, so types of radioactive decay. Now, this is where the bulk of the slides are, where the problems, because we're going to break down each of these, because now we're going to start balancing equations. Remember balancing equations and all that fun? Yes, that's what we're going to be doing now. So I'm just going to briefly introduce these, but each of these has its own slides. So Rutherford discovered 3 types of rays emitted during nuclear decay. There's alpha rays, and it has a charge of +2 and a mass of 4. I'm going to break all of these down with examples to show you. And we now use this as a helium nucleus. So I'll go into what that means. But if you look at periodic table, that helium has a mass of 4 and it has a proton number of 2. So if you look at that, that is why we call it a helium nucleus, because it matches that identically. Beta rays have, and you should become familiar with these symbols that go with this as well. If you're going into organic chemistry, you will understand alpha and beta in a different way, because there are alpha carbons and beta carbons and gamma, but they're not used in radioactivity. But you will see these symbols again, depending on how far you go into I believe it's the last organic that you start getting into this. I know alpha beta because I'm an old person, and there was a big supermarket back in the 70s and 80s called Alpha Beta. So that's when I always see this. That's what I can't help but think about, because that's where I used to shop all the time. Anyways, have a charge of a beta rays has a charge of -1. Don't worry about the Cu right now. And it's a negligible mass, which means it's got 0 mass. It's just got a -1 charge. And the one thing I don't like about the slides is it doesn't show the symbols for these, but I have more than enough to go over this with and show the symbols at the same time. And then gamma rays, form of light energy. It's not a particle like alpha or beta. It's just light energy. In addition, some unstable nuclei emits positrons, which are the exact opposite of an electron. So it's a positively charged electron. And then we have an unstable nuclei which undergoes electron capture, which is also called K capture, capital K capture. It's a low energy electron. It's pulled into the nucleus and changes. I'll go into that later. Okay, so one of the things you definitely need to understand and be familiar with is what's on this page. This is a slide that's given from your book. So I use other slides from other stuff, but this is from yours. And the other slides will definitely show this, but there'll be little minor differences. When you're balancing the equations that we're going to cover, this is where these nuclear symbols are going to come in. And if you don't know how to do these, you're stuck. So this is a page you definitely need to be familiar with and what they represent. So let's go through. We have a proton, which is a P with a superscript of a plus. And it either can be written as a 1/1 and an H, or a 1/1 and a P. We have a neutron, and a neutron with a 0 because they're neutral. And it is 1 with a mass of 1, and no proton, and then an N. Electron. This is a symbol when it means a negligible mass. That's what this is. It's 0 with a mass, a -1 charge, and an E. We have alpha. Here's the alpha symbol. And it's either as a 4/2 with an alpha sign, or it's a helium sign. Both of these mean the same thing. Beta is either a B or B minus, and it is either a 0 with, these have no mass to them, or it could be a beta sign with a -1, or -1 and an E. And the positron is a B, a beta plus. And as you can see, it's the opposite of electron. So it has 0 mass, but it has a +1 charge. I found this online, and I think it gives and it describes everything. So I like this because it's colorful as well. And you can see the symbols. It's giving the symbols too. So you can see what all of these mean. So I have a lot of just different slides. They all have the same information, but some of them explain it a little bit better than others. So for instance, this also telling you the charge on this, because when you're first learning some of these things, it's a little difficult to retain it and keep it separated. So you can refer back to some of the slides that are a little bit more clear to understand than other ones. All right, so write the symbol for each of the following types of radiation. I don't expect you to know this yet because I haven't gone through them. But an alpha particle is... I kind of just skipped through. So what is an alpha particle? We're writing it as helium. So mass of 4, proton number, atomic number is 2, and a symbol is He. A positron is the opposite of an electron. So you're going to have a +1 charge, 0 mass, and an electron. And a beta particle has electron, -1, and 0 mass. So now what's going to come up with these is nuclear equations. We need to know the symbols because we have to show what's happening. Just like when we learned them the other time, the other way with actual when we're not dealing with nuclear chemistry, you have to balance. These also have to balance, but they have to balance in a different way. We have to make sure that what sums up on one side sums up on the other side. And remember, when we start changing atoms, you have to make sure that all of this matches up. So let's break this down. Here we have a parent nuclide. And when it starts to basically separate or decompose, if that's what, it emits energy, it now has a daughter nuclide because this came from this parent nuclide. And it has the energy, the particle that was emitted. In this case, this is an alpha particle. So what are we looking at? Well, the atomic numbers have to equal. What do I mean by that? If they're changing, well, this is 92, so this has to be 90 and this has to be 2. So the bottom ones have to match up with the one on this side. The top one has to match up on the top. So here we have a mass of 234, but a helium mass is 4. So we're going to subtract that. That means that this has to be 234. We look at this atomic number on a periodic table and we can figure out the rest of it. So everything matches up. The sum of the mass numbers for the reactants is 238. The sum of the mass numbers on the product side is 238. The sum of the atomic numbers on the reactant side is 92. The sum of the atomic numbers on the product side is 92. So this is just getting started. It might seem confusing. This is why I have actually a lot of problems on here to help get you more familiar with this. All right, so if you looked at it, this is my slide from my class, and you can see that it breaks that down even more. It shows you what the neutrons are, what the protons are, what the neutrons are, and what the protons are. And hopefully this helps you understand. Now this is 2 and 2, but remember the mass is made out of 2 and 2, which is 4. So this hopefully helps you understand how this is happening here with the alpha. Alpha particles are the easiest ones to understand. So that's why they're introduced first. They're also the big behemoth giant out of all of these. But this is exactly what a balancing equation looks like. Whatever you have on this side has to be balanced on this side. So with helium, the helium alpha particles, it is a nucleus. The mass number decreases by 4 always, and the atomic number decreases by 4. All right, so now let's do another one here. So the general equation is a radioactive nucleus, and then here's the arrow, the new nucleus, and then the radiation. And whatever's on this side has to balance on this side. So if we look at this one here, we have another alpha particle. We start with 251, so that means this on this side has to equal 251. So if we take 4, subtract 4 from this, we can look up, we can get the mass. And then here, here's the 98. We subtract 2, which is 96, so we can look up and see what this is because we have the atomic number. And we already know it's alpha particle. So everything here matches, but this is the general equation of all of these that we're doing. This is not going to change. Okay, so alpha decay. Again, I'm showing you a lot of slides on the same information just to keep it repetitive. So an alpha decay is the nucleus ejects an alpha particle, so its mass number again decreases by 4, and its atomic number decreases by 4. So that's what you're seeing. But you start off with the parent nuclide, and you end up on the product side with the daughter nuclide and the radiation energy. It's also the most ionizing type, and I think that's because it's just so huge. It comes into contact with more stuff where something that's very small will not. So it's the most ionizing, but it's least penetrating. Because it's so big, it's kind of, think of it as slow, so it doesn't take much to stop it. So here again, it's just a regular picture. These are all repeating itself, but I wanted to give enough pictures to help show and understand. So you can see this alpha particle, it's got 2 and 2, so that's what you're seeing here. It's coming off of this. I told you I'm just giving you more and more of the same thing pretty much, but I'm hoping that this helps make sense of each one. Okay, so let's do an example of an alpha particle. Complete the following nuclear equation. So you're given all the information for the parent nuclide. We don't know what the daughter nuclide is, but we know what the alpha alpha decay is. So this just basically comes down, you may be asked to be given a nuclear equation. So you may not even be given this, but you would be given this. So try to imagine how to set this up and learn from these equations. These lectures, I told you, are from a different chemistry. So I kind of like them because they break it down a little bit easier than just throwing it at you. So you can see if you're given this and you're not given the nuclear equation, start understanding how to put this together. You're told that it's a alpha particle, so you know what this looks like. You can pull this information and write it here. Given a periodic table, you can see what the atomic number is. There's an arrow, and you have a question mark. So we have to figure out what the daughter nuclide is. So there's different ways to do it. This is kind of breaking out step by step, which is nice. So you take 241 and you just solve for the question mark, and that is 237. Now we need to solve for the atomic number. We do the same thing for the bottom one. And now we have enough information that we can plug that in, look it up on a periodic table, and plug it in. So hopefully this makes sense. It may take a little while because a lot of this is being thrown at you at one time, but this section really is not as difficult. You just have to learn the symbols. You have to learn what type of radiation is what, the key words to go with it, and how to write the isotopes. Ionizing power, I kind of already discussed this. I'm just briefly going to go over it. It's the ability of radiation to ionize, and alpha radiation is the highest, and I think it's because it's so big that it comes into contact with more. So the more molecules and atoms it comes into contact with, the more it can ionize. However, it does not penetrate through matter the way that other radiation does. It's the slowest one, and it can be stopped very easily by a sheet of paper. So it doesn't do, except for the only time that this is really dangerous is if it does come into contact inside your body. Because it's so big, it can do more damage by contacting other molecules. And now we're dealing with beta decay. Beta decay is a neutron that a neutron becomes a proton by ejecting an electron. So that's what we call a beta particle. So the mass number does not change, but the atomic number increases by 1. So in this case, you can see that we start out, so it's about 10 times more penetrating than alpha, and I have a picture to show all this. The atomic number increases by 1. You can see it goes from 88 to 89, and the mass number remains the same. So that's what this represents. So if you look at these, match these up, and you should be able to determine and see what's actually happening here. So this one may seem a little weird because it's like, okay, well, it's increasing in the number, and it's also emitting an electron. The best I can explain to these is just to learn what these actually represent without overthinking it, because I think if you overthink it, it's going to get very confusing. So just go straight with what it's telling you. Atomic number increases by 1, mass number remains the same, and when you add these up, you can see 28 on this side, 28 on this side, 88's on this side, and it increases by 1. So this must mean 89, and it has to, because this has to balance on this side, and 89 minus 1 equals 88. So beta decay, here it becomes a neutron becomes a proton, and it also ejects an electron at the same time. So that's what the beta particle is. This is from my slides on the other, so I'm just showing more and more of the same stuff. This one actually breaks it down here though. 8 neutrons, 6 protons, 7 and 7. 0 neutrons, 0 protons, but a -1 charge. So let's do one of these other problems again. So write a balanced nuclear equation for the decay of potassium-42, a beta emitter. So if you're asked to write a balanced nuclear equation, we have our unstable isotope on this side. We have our arrow, our question mark for what we're trying to solve. And we know you have learned the symbol for beta decay. So once you plug those in, you should be able to do the math and do the same thing with these. And always just keep a list of what that's supposed to do. So you know that the atomic number's got to increase by 1. So these are the things that you just need to keep track of to make sure you're doing them right. So if we solve for this, the mass number is 42. Here, determine the atomic number. So if you can see the math, we're solving for the question mark. So atomic number now is 20, which increases by 1, which is exactly what we wanted. And it's calcium-42. We can plug all that in, and that's giving us our balanced equation for this. Gamma emission is high frequency energy photons of light. So gamma emission is very different from alpha or beta particles. It has no charge and no mass. It's a form of electromagnetic radiation. It's on the spectrum of, remember when we were looking at, if you've studied chemistry, when I think it's 111 of UV, visible, and so forth. It's on the end of the electromagnetic radiation spectrum next to X-rays. And with this one, so one thing I want to point out when you're dealing with strictly gamma radiation, the identity of the element does not change because it doesn't have mass, and it doesn't have a mass or charge to it. So had this been just a regular equation here, we would have it's 0 and 0. It would just be a different form of the same element, but it's a lower energy form of that parent isotope. However, gamma radiation is usually emitted in conjunction with some other type of radiation. So in this case, it's showing you the alpha particle. The alpha particle is why this has changed into a new element, not the gamma radiation that has occurred. Because if it's just that, it's a 0 and 0. It would just be a different form, a lower form of the same element. So in this case, you can see that it's been emitted on here, and that's what it's saying. Other types of radiation. So this is what this little this energy arrow is that it's because it doesn't have charge and it doesn't have mass. This is a perfect example from another one of my pages of what I'm talking about. The gamma radiation, you can see it's just a different, M is for metastable, so it's not stable as this form. However, once the gamma radiation has been emitted, it is now a lower energy form of the same element. So that's what I tend to, that's what I was talking about here. That for these, it's no charge, no mass. It just tends to be a lower energy element of the same element. And here it's changed because of the alpha particle, not because of the gamma emission from it. Okay, so if the room next door contains an alpha emitter, a beta emitter, and a gamma emitter, all with similar activities, which particles are you likely to detect in the room you're in? Well, I haven't really covered this yet, but it's going to be gamma rays, because gamma rays can go through anything except for concrete and thick lead. Alpha particles can stop with just a piece of paper, and beta particles can be stopped by lab coat, gloves, and thin aluminum. So both of those can be stopped, but they both can do severe damage once inside the body if it's ingested. But gamma rays are the ones that can penetrate mostly anything. So here's a slide from my other class. This is not in your book, but it gives a good indicator of what. So alpha particles, you can see pretty much stops there. So as long as you're not ingesting it, it stops just with the resistance of your clothes. Beta particles can go in a little bit more, but if you're wearing a thick lab coat, it's not going to do much. And gamma can go all the way through. You need some thick lead or thick concrete to prevent that. So here is ionizing radiation strikes molecules in its path and knocks away the electrons in the molecules, forming unstable ions, which could be radicals, causing undesirable chemical reactions. This damages the cells most sensitive to radiation, and that causes rapidly dividing cells in bone marrow, skin, and reproductive organs, thus causing cancer. So different types of radiation can penetrate the body to different depths. This is not in your book, which is weird because they gave me the slide, but I can't find this picture in your book, but you can see the depths to you can see this one goes to just a very small 0.01 millimeter. This can go to 1 millimeter, and this is going to 100 millimeters. So you can see this is a thick lead. I think they could have did a better picture of this, but that's what they gave me. So I think this kind of explains it a little bit better of where the distances are. So positron. Positron has a charge of +1. It is the opposite of an electron. So it's an antiparticle is what they call it instead of opposite. It's an antiparticle of electron. It's similar to beta particles in their ionizing and penetrating abilities. When an atom loses a positron from the nucleus, its mass number remains the same. That's why you see a 0 there. And its atomic number decreases by 1. So a positron is an antimatter, that's another word they use, equivalent of an electron, has all the same properties of an ordinary electron, except that it has a +1 charge instead of a negative charge. And it results from a proton changing into a neutron. So again, here we have phosphorus 30, and we have a positron, so the mass stays the same. However, as you can see here, an atomic number decreases by 1. So this is 14 on this side. This is +1. This makes 15. This makes 15. So you could solve it the same way I had shown you with the examples I took from my other class. It just solved for the question mark there, and then you can figure out that would be 14. So again, here's more pictures of showing what it does. And this is from my other slide from my other class. So you can see another example of 24 + 1 = 25, and 25 is on that side, so these balance out. And if you want the general form, I think this also helps you here if you needed to look at this for the positron. An electron capture it's also called a K capture. It occurs when an inner orbital electron is pulled into the nucleus. No particle emission, but atoms changes. Same result as a positron emission. This is a kind of weird one. So what is this? It's known as K capture as well. The nucleus draws one of the atom's inner core electrons into the nucleus, converting a proton into a neutron. The electron that is drawn into the nucleus is shown as a reactant in the radioactive decay. So as you can see, it's as a reactant on this side. It's not on the product side. So that's what makes this a little different, because it then produces, where everything's been on the opposite, where there's been one reactant and two products at least. Now we're showing two products and two reactants and one product. I hope I said that right. So when a proton combines with an electron to make a neutron, mass number stays the same. You can see we have 92 plus 0 equals 92. Atomic number decreases by 1. 44 minus 1 equals 43. And you would solve this the same. Once you know what it is, you have the question mark, you can do the math on this and solve for it, but you have to make sure you have the right radiation symbol here. So they're not difficult, but you just have to keep them all straight. So here is another example. I have found a general formula for it to show you. And the balancing atomic number is 37, minus 1 is 36, 36 on this side. Balance mass number is 81 and 81. So nucleus captures the surrounding electron from the inner core. Electrons effectively turns proton into a neutron. Atomic number decreases by 1, but the mass does not change. This is in your book, so here's a whole chart of each one and giving an example to break it down, which I think is good. Here you can see this is the M, that means it's metastable, but then it goes into actually lower energy stable, but nothing really changes with it, and it's just showing the gamma ray, because gammas, remember, no charge, no mass to them. So this would be really good to look at if you're having a hard time understanding, keeping these straight. All right, so let's do some problems. So we have Ti-210 decays to lead-210 and one other product. What is the other product? So even if you didn't know what the other product is, we can look this up on the periodic table to determine what the atomic numbers are, and we can see that the mass didn't change. So that gives us enough information to try to figure out what this is. Plus you have tons of charts and lists that I gave you, so that could also help by looking at that. So the first thing you got to do is balance the nuclear equation. So we need to set it up with the question mark if you have to. And we can then look up these information. And I'm just realizing now that they gave me the wrong one for this. Look at what they're saying that this is 210 lead, but now they have it as 2H. Sorry about that. I sometimes do not catch these things because I'm looking at numbers and not at the elements. So let's pretend this says 2H, TH on it, and not lead, because that's what this is supposed to say. And okay, so we have the mass doesn't change, so we know there's going to be a 0 here. But what we noticed here is that there's an 81, and this is 82. So this has got to be a -1, because the 81's got to balance on both sides. And this can't change anymore because we don't have anything else on it. So that's where the -1 comes. So now we've got to figure out what it is. It's a beta particle. So this is going to be a beta particle for this. And once you look at the list, you can see what these things, we can go into the more information to see what this is. And if you have your list, then you can then figure out what type of radiation this is. Hopefully these are right now. I didn't look at these either, so keep your fingers crossed. So now you're given enough information here. Let's try to figure out what these are. I think they're all on the same page, and they are. So once you can do the math, you can start plugging these in. I strongly suggest maybe you start on this page before you look at the answers and see if you can plug these in when you start getting more comfortable with understanding it, and see if you come up with these answers. And if you do, then you've got it down, at least, or keep enough good notes around you that you should be able to plug this in and figure out what's going on here. So we have the beta particle, we have our alpha decay, beta decay, excuse me, that's electron capture. And then we have our positron decay. So as you can see with some of these, it just is a matter of becoming more familiar with them. All right, these are taken straight from your book. These are the examples that are in your book. So they've got a lot of words. I kept everything just because I think it helps explain if you're getting stuck on some of the stuff. So this is why I said there's a lot of slides, just because I'm giving you everything that it says. Write the nuclear equation for the alpha decay. This is a lot of stuff on it, but it's still same to the similar one that I showed you in the beginning. So just simply do the math. Solve for the question mark. And if you solve for the question mark, you can plug that in, and it'll, you already know what the alpha particle decay is. So if you do the math right and then check what it's supposed to be, the math should be okay. It should all balance out. Same here. Write the nuclear equation for these. These are giving you for beta decay, positron emission, and electron capture. Again, I've broken all of these down. I've kept it intact with what is in your book. So it's just a matter of going through these again and just being comfortable with them. And then I found, this is from my other lecture. It doesn't cover all of them. That's the only problem, is what's covered in this, your 112. Mine is from 103. This slide is from 103, but it does give a few of these. So it breaks down what you should expect, what the radiation is and what the emitter is, and then what you should be looking for at least 4 of these. And that might help clear up some of these that might seem confusing. Okay, so the chemical environment of the atom makes no difference to the process of radioactive decay. Pure uranium-38 metal or uranium, is any one of its compounds undergoes nuclear decay in the same manner at the same rate. There's no way to control natural radioactive decay. It cannot be sped up, slowed down, or prevented. So it just spontaneously happens on its own, and it